Hello and welcome to another presentation in the Networking at Scale conference. My name is Joseph Beshay, and I'm part of the Traffic Protocols team here at Meta. During the next 20 minutes or so, I'll be sharing our experience using QUIC to improve the transfer times of requests in Meta's backbone network. This is one of the great examples of how QUIC enables simple solutions that result in significant wins. But first, I want to give a shout out to my colleagues, Andre and Matt, who have contributed heavily to this project. My talk will proceed like this. I will give a high-level introduction to what the problem is, how we currently solve it, and how we are attempting to solve it using QUIC. So the Meta backbone network looks roughly like this. You have servers in different regions, distributed all over the world, connected using dedicated links that we closely control. These servers have different content, they have different functions, but a common thing between them is that they communicate with a specific pattern that repeats over and over again. And it's something like this. You have two servers communicating over HTTPS to transfer some kind of data. If you look deeper into what each of these connections looks like, we start with a TCP handshake, and then it's followed by slow start. The TCP handshake establishes the TCP connection, slow start grows the congestion window. While slow start is happening, the TLS handshake is also taking place. And by the end of the TLS handshake, the secure connection is established and we can start transferring secure data between the peers. If this connection lasts long enough, we also go into congestion avoidance. In this case, we're looking at QUIC as the congestion controller. The thing is, this whole process repeats for every single connection. So let's take a deeper look at these stages. So if we look at the handshake, if we begin by looking what happens inside the handshake, it looks something like this. We have two servers, and in case of TCP and TLS 1.2, we have one round-trip time for TCP connection to be established. After that, two round-trip times to establish the TLS connection. And at this point, we start transferring the HTTP data, which is the transfer between the client and the server. We can do better than 3 round-trip times, though. If we're using session resumption in TLS 1.2, it looks something like this. We have one round-trip time to establish the TCP connection, and then one round-trip time for TLS, and then we can start sending HTTP data. We can still do better than that using 0RTT in TLS 1.3, where the HTTP data can be sent immediately in the first flight of data in the TLS handshake. We still have the TCP round-trip time, the TCP handshake at the beginning, and you can also get rid of that using TCP fast open, although this has a lot of issues and it's not widely used on the internet. You've heard more from Jana about that earlier today. With the handshake out of the way, let's take a look at the data transfer. The data transfer, now we're in the HTTP after the handshake has completed, and we start by transferring, let's say our initial window is 1 packet, we send 1 packet, and then after that is acknowledged, we send 2, and then 4, and then 8, etc. Basically what's happening is the congestion window is growing exponentially. And it's important to realize that until the congestion window has reached the bandwidth delay product of the connection between these two peers, we are not utilizing all the available bandwidth. We're simply probing for that, and when the congestion window hits the bandwidth delay product, this is when we're using all the available bandwidth. So you can look at it as a connection spends time in these different phases, the handshake, the slow start, and then the congestion avoidance. If you graph this, it looks something like this. So what you see in front of you is an experiment between a client and a server that communicate over a 500 megabit per second link, and the round-trip time between them is 75 milliseconds. The x-axis is the transfer size, which is in log scale, and the y-axis is the percentage of time spent in each of these phases. So the yellow part is the handshake time, the red part is the slow start, and blue is the congestion avoidance. Until congestion avoidance, until the blue part, we're really not using all the available bandwidth for any of these connections. So if, for example, you take the 10 kilobyte transfer, a connection that transfers 10 kilobytes over this link spends 60% of its time in the handshake, and 40% of the time in slow start never gets to use all the available bandwidth. even if you go all the way to 1 megabyte, you're spending roughly 17% of the time in the handshake and 83% of the time in slow start, and again, never fully utilizing the bandwidth. Not much better at 20 megabytes, where you're roughly using 80% of the time in the handshake and slow start and only using all the available bandwidth for 20% of the time. This graph uses an initial congestion window of 10, which is the default in the Linux kernel right now. And if you look at this graph, increasing the bandwidth shifts the whole graph to the right. So if we have more than 500 megabits per second, you will just see more yellow and red and less blue. And this problem is not new. The researchers looked at this for many years, ever since TCP existed. Some suggested that the sender caches the congestion window and reuse it when it's talking to the same server, or send it to the server to use it. The paper in the middle, for example, suggested that in controlled networks, you can completely skip slow start and use what they called jump start, which is where we got the name jump start and adopted it and tried to do something similar in QUIC. And there are many more approaches, for example, using BPF to set the initial congestion window, or many other approaches that were suggested for satellite links that have very high round-trip time. The goal is basically to achieve the full available bandwidth within the first flight of data. So how are we solving this right now? What's our approach to it at Meta? We have servers located in different regions. We simply add proxy servers in each of these regions, and each of these proxy servers maintains a number of long-lived connections to each of the peer regions that it talks to. Basically, we are trying to achieve connection pooling. By using connection pools that stay active all the time, we are able to cache the congestion window to be used by over and over again for more than one request. So in this case, when a client in California wants to connect to a server in New York, it talks to its local server. This is over very low round-trip time, so we're saving the handshake delay. And then the proxy server talks to the proxy server in New York, to which it already has a connection with a high congestion window, and that destination server talks to the server in the New York region. The only thing is that it's a complex process to maintain these servers. Every time the server starts, any of these proxy servers starts, it has to prime the connection, maintain this connection pool, and grow its congestion window, and make sure that it's always available for use immediately when it receives any connection from a client. So the question we asked ourselves is, what can we do with QUIC? Can we make this better for our services at Meta? And here's what we tried to achieve. We're creating what we called QUIC Jumpstart. And our goals were to achieve congestion window caching and avoid excessive bursts on the network, just not dumping a lot of data at once. And we want to do both of these while being aware of the peer region. Links between different regions have different available bandwidth and different round-trip times, so we want to be able to keep some sort of state for each pair of regions and use that over and over again. And we want to do all of this with minimal explicit coordination between the different parts of the service. So here's how we do it. We maintain a per process state that includes a congestion window and minimum round-trip time seen for each peer region. Whenever a QUIC connection ends, we update that state. And what do I mean by that? We just look up the region of the peer we were talking to during this connection, and then we take the congestion window and the minimum round-trip time, and we maintain an exponentially weighted moving average of these two. Next time a connection is starting, we just look up the region of the peer we're about to connect to, create a new congestion controller with the cached congestion window and the round-trip time, and then to make sure that we don't dump all of this data at once into the network, we set the pacing rate so that it is slowly written to the network at the pace we expect the link to support. What practically happens is large transfers grow the congestion window. So at the connection end, these are the ones that put higher values. And when small connections are starting, they just use the available congestion window that has been built up by one of the large transfers, and they rarely experience congestion or get a chance to update the congestion window again. So the speed at which we converge and we find the congestion window to be used between two specific regions depends on the distribution of the size of the requests that we have experienced in this process. The more large transfers we have, the faster we converge to the right congestion window that should be used, and the faster we react to any changes in that available capacity. So that's for quick jumpstart that allows us to avoid the time spent in the slow start phase. What about the handshake? For this, we already have quick zero RTT, which we have heard about earlier, where simply you are able to send the quick initial packet and immediately send quick zero RTT data packets within the same flight. And as Jana mentioned earlier in his presentation, this has an advantage over TCP fast open because you can actually send arbitrarily as many packets in that very first flight. So we took quick jumpstart and quick zero RTT and decided to deploy them in one of the services in Meta's backbone. And this is what we noticed. Requests under 1 megabyte were 10% faster when using quick jumpstart and zero RTT compared to the double proxy approach. As requests grew larger, that advantage started to dilute, and eventually around 8 megabytes, which is the size of a lot of objects in this specific service, we noticed that we were roughly 30% slower. Quick jumpstart and zero RTT were 30% slower than the double proxy approach that I explained earlier. This is for the tail latencies of both approaches. The more we looked at it, we realized that the problem is not really in jumpstart or zero RTT. It turns out that our quick implementation gets CPU bound before TCP. Our implementation has been significantly tested and used in the internet between our clients and our servers, but when it comes to the data center with much higher bandwidth available, we needed to take a fresh look at the performance of our quick implementation. And we immediately identified two areas for improvement. The first was to tune the ACK frequency. We realized that we are spending significant valuable resources in the quick transport processing ACK packets. So what we did is we decided that for larger requests, we would use a lower frequency of ACKing so that we allow the transport to spend more time transferring packets rather than processing ACKs. And in the same vein, we used generic receive offload so that we would read more packets from the network at once and process them at once without incurring the overhead for one packet at a time. And with these two changes, we reran our experiments again, and we found out that we are still able to achieve the 10% improvement for requests under 1 megabyte, and now we can match the double proxy approach for requests greater than 8 megabytes as well. So this is the setup we're currently using to expand our deployment of quick jumpstart in services within Meta's backbone as we track the congestion signals and see how much we can improve the performance as well as maintain the congestion levels of our network. What we're practically doing, if we look back at the graph from earlier, is we're moving this blue area down to the bottom left corner. We're expanding it to the bottom left corner. What is now happening is that we are now able to use all the available bandwidth from the very first flight in the connection. So this is great, and we're looking forward to expand it more. But what are some of the issues that we anticipate to happen as we continue to expand? The first thing is that the idea of having this state be per region is a little bit simplistic. Sometimes we have multiple paths between regions. For example, if you have two paths between a client and a server, just averaging the congestion window is not enough. If the link bandwidth is significantly different, the average is not accurate for either of them. So to address this, we're looking into making jumpstart path aware rather than just peer region aware. The second thing is that quick jumpstart and averaging the congestion window state might lead to a slower reaction to congestion events. When you consider the impact of a packet loss event on the congestion window of a single connection, you realize that by averaging this value and maintaining it in the per process state, we are dampening this signal. So effectively, it will take us more packet losses in order to reduce our congestion window by the same amount. If this becomes a problem as we expand our deployment, we are considering to factor in packet losses when calculating this updated congestion window that we store in the per process state. The third thing we're thinking about is the more we roll this out, the more processes will have this individual local state of the link. And the request distribution between these processes, or running on the same or different hosts, is going to significantly impact the accuracy of their pictures or their views of the state of the network. If one process gets a lot of large requests and the other one does not have any, then the one with the large requests is going to have a more accurate view of the network than the other one. And if these large requests do not overlap at the same time, then both of them will not have very accurate views and could have an aggregate congestion window that is higher than what the link can actually sustain. So what we intend to do is, if this becomes a problem, to add some more centralization to maintain a common picture of the available bandwidth on each of these links that different processes can use. But back to what we actually achieved with what we have right now. So this is the picture we had earlier from the current solution that we have. The double proxies with long-lived connections between them. What QUIC Jumpstart and Zero RTT allow us is to remove an entire service from the picture with its mesh of persistent connections, yet still maintain the properties we were getting from connection pooling through these servers. Using QUIC Jumpstart and QUIC Zero RTT, a client in California can talk to a server in Texas by just starting a QUIC connection and still be able to achieve the bandwidth, all the available bandwidth immediately. Same for a client in California to a client in New York, just a direct connection without depending on any intermediate services. The nice thing is that we can achieve this high efficiency without the cost of the complexity of maintaining a whole service. QUIC allows us to simplify our system and still achieve the same efficiency. It is worth noting that establishing individual QUIC connections incurs a little bit of CPU cost, but the CPU savings from removing a whole service is more than enough to cover for the additional work of establishing these additional QUIC connections. We are looking forward to expand Jumpstart deployment to other services in our backbone network to improve the performance of cross-region traffic for these services and come back and share more results. So in summary, QUIC Jumpstart and Zero RTT offer us a simple yet effective solution to achieve low transfer latency without adding external dependencies. And since this is all built on top of QUIC in the user space, we can iterate on it much faster and keep adding new features and improving our algorithms. Thank you very much for joining me, and I look forward to answering some of your questions.